Right, I think we're online. Okay, so welcome to Yebo Tutor. This is our chemistry session. I'm Yasha and I'm here to have fun with you, working out some problems on chemical equilibrium. Okay, so we did some calculations last week on acids and bases, but then we had some questions during the week. So that's how we will function, and we've always said that we are interested in getting your questions. So one of our students just requested that we go through the basic calculations in chemical equilibrium. So let's hear it. Right. So what we have are basic questions. We're going to build the calculation stage. As you know, your chemical equilibrium, it has a few topics that fall under it. So today we're just going to look at the calculations, because the question had to do with calculations based on chemical equilibrium. So let's work these out together. I'll put up the question, and then you can read the question, start to work it out as I look for the necessary information. Right, this is going to feed into acids and bases, so let's make use of it. Right, so that's our first question. Our first question is a very straightforward question. So all these questions are arranged in such a way that we will have an introduction to the chemical equilibrium concepts, right? So attempt the question, please. Let's attempt the question while we look for the answers. Attempt the question. Then we will compare our answers. Yes, our answers. There we go. Okay, so attempt the question, then you compare answers. I'm just putting up a comment there. Good. So the first question reads as follows. This is about writing expressions for the chemical equilibrium constant. As you know, chemical equilibrium is all about chemical reactions which take place in the forward and the reverse direction. So it means that you can actually write two chemical reactions to represent what is taking place. In other words, this is a set of, it's a reversible chemical reaction. If it is reversible, it means it can take place in the forward. So you've got 9x gas plus y3 gas. They react to form 3x3y gas. So this is the forward direction. But this chemical reaction also is reversible. So 3x3y gas also dissociates into 9x gas plus y3 gas. So these are not elements that we know. This is just an example that will guide us into how to express Kc. So that's the first question there. So if we have this, let's not forget that this is a stoichiometric ratio. So we have a stoichiometric ratio of 9, and we have a ratio of coefficient, and then we also have a coefficient of 3 there. So in this chemical reaction, we have those molar ratios. So let's now build the expression for the equilibrium constant Kc. We know that the equilibrium constant Kc is a ratio of what to what. So if it's a ratio, it's simply written as dividing two quantities. The top quantities there represent the products. The bottom quantities there represent the reactants. So we are looking at the concentrations of the products, whichever number of products that you have, and the concentrations of the reactants, if there's 1, if there's 2, it depends on what's available. So in this case, in our question, the reactants are the X gas and the Y gas. The product is the X3Y gas. This means that the first thing is we've identified the products and the reactants. The second thing is, what is the state, the phase of these elements. If an element is either in its pure liquid or solid state. I'm sorry, I have to decline this. Right. So if an element is either in its liquid or solid state, then it does not qualify to be part of our equilibrium constant calculations. So in our case, we have gas. We have that as gas. Right. I just need to stop this person. And then we also have that one as gas, right? So in our numerator, we will write the concentration of the product. In this case, we have just one product. That's our X3Y. And we will use its molar stoichiometric ratio. That will be the coefficient 3. And it becomes the power to which we raise the what? The concentration. This is all divided by the concentration of X raised to the power of 9, and then multiplied by the concentration of Y raised to the power of 1, which we often actually do not write, isn't it? If you are raising something to the power of 1, you do not write that you're raising it to the power of 1. Okay? So this is an expression, isn't it? This is an expression of the equilibrium constant Kc, where we have our product, the concentration of the products at the numerator, the concentration of the reactants at the denominator. And we always look at this one as we are looking at the forward reaction. That's how we express this. So this is the first part. Did you all get it? I hope you did. So we've got our X3Y as our product, and it's raised to the power of 3 because we've got a 3 there. And then our X is raised to the power of 9 because we have a 9 there. And then our Y is raised to the power of 1 because we have a 1 there. So it's actually Y3. Okay, so I guess this one was an easy one, isn't it? So let's step up a bit. What are the things that we picked? We picked the equation, and then what is the next thing? We picked the states, right? The states are very important. So let's jump to the second question. Let's jump to the second question. And I'll give you a second to respond to this question. Right, the second question is from an exam paper. The second question is from an exam paper. The question reads as follows. So you can find out which exam paper it is. It's recent, right, in the past 3 years. So the question reads as follows. The expression for the equilibrium constant Kc of a hypothetical reaction is given as follows. So this is now the reverse. So you've got Kc is given and you've got all those. Which one of the following equations for a reaction at equilibrium matches the above expression? Which one of the following reactions, which one of the following equations for a reaction at equilibrium matches the above expression? So let's attempt it, let's see. Let's attempt it, let's see. Let me give you 2 minutes to 3 minutes to figure it out, and then we can have fun. done? Have we found an equation which it's a hypothetical equation, right? So it represents, or it is the equation from which this equilibrium constant was found or calculated or expressed. Right, so I think that we've had enough time to look at it. First one, is the first one a candidate? In the first one, in fact, from this, we can tell that these are the what? These are the reactants. We can tell that this is the product, right? So the chemical reaction, it certainly must have 2y somewhere plus z somewhere, and it's in equilibrium with 3x somewhere, right? So these are our reactants, and we are using the power there. We know that we take it from there. The power there is 1, isn't it? So this is our z, and then our power there is being found from that part. Okay, so if we have a chemical reaction which is like this, it's obvious these are either gas, aqueous, gas, aqueous, gas, aqueous, and not liquid or no solid. Right, so this is the chemical reaction, and we're looking for one that looks like this and qualifies. So let's look at the first reaction. The first reaction, it has our Z, right? So maybe let me rather put this one up here so that we can use it. And then I use this one to then find the correct one. So we do have a Z, right? Or a Z plus 2y, which is fine on the right hand side with a 3x. Okay. So there's a possibility that this could be our answer, right? So you tell me, is A the correct answer? Would you give A as the correct answer, right? So you tell me, is A the correct answer? Right. Is A, so let me put it in brackets, the correct answer, right? So I just want you to tell us, is A the correct answer? Tell us. You can see the poll on YouTube. The next one is Z plus 2y, right? The next one is another Z plus 2y. Z plus 2y is equal to 3x. So this one is a candidate again, right? This one is a candidate again. We actually have our Z, we actually have our 2y, and we have our 3x. So it's a candidate, right? Next one is, okay, so this one is out, isn't it? This one is out because we have a Y2 gas, right? So it's a diatomic gas, but the stoichiometric requirement is that it should have a what? The ratio of moles is supposed to be 2 as to what? As to 1. 2 of Y as to 1 of Z. So it doesn't qualify. So this part C is out. How about part D? Part D has a Z plus 2y, so it works. Oops, sorry. Where are we? Yes, we're here. And then it has a 3x and a q, there's a q there. So part D, it does have what we're looking for, right? Part D is what we are looking for. Part D is what we're looking for. Right, so of these three, A, B, and C, which one is the correct one? As of these three, A, B, and C, which is the correct? Which is the correct? Right, let's relook at A. A, this is in the gas phase. It qualifies to be part of our equilibrium calculation equation. 2y is in the gas phase as well, but 3x is in the solid state. So this A is out. The molar ratios are correct, but we exclude all these elements that are in the solid or in the liquid state. How about B? Aqueous qualifies, aqueous qualifies. This is in the liquid state, so it's out. So what are we left with? Aqueous qualifies, aqueous qualifies, aqueous qualifies. This is in the solid state, so it's not going to be part of our equation. So in our numerator, we will only have x raised to the power of 3, which is the concentration of x raised to the power of 3, which is what we have there. So part D becomes our correct answer. Part D becomes our correct answer. because this is not going to be part of the equilibrium constant calculation. Now Kc will simply be the concentration of X raised to the power of 3 divided by the concentration of Z multiplied by the concentration of Y squared, which is in agreement with our equilibrium constant expression. Right. Any questions on this one? Any questions on this one? Right. If you have a question, you can just drop it into the chat, then we can discuss. So we have finished. We've looked at the expression of the chemical equilibrium constant from two sides. Number one, we looked at it from a given equation. Number two, we derived, or we came up with a given equation, or we selected the correct equation from a given equilibrium constant expression. So it's important for you to be able to just flip between these two in any way that is necessary. Depends on what you've been asked, isn't it? Okay, so let's jump on to the next question. Let's jump on to the next question and see what's in store for us. So these are chemical equilibrium calculations, right? These are chemical equilibrium calculations. Right, the next question is about calculating a reagent concentration. So these questions will come in different shapes and sizes, and they will come from different angles. So this time now, besides expressing, right, or deriving the expression of an equation, now you are calculating reagent concentrations from the chemical equilibrium constant, right? So let's see what this question says. This question says, for the reaction sulfur solid plus oxygen gas is equal to sulfur dioxide gas. Write the expression for the equilibrium constant, and then number two, calculate the equilibrium concentration of oxygen. If Kc is that and the concentration of SO2 is that at equilibrium. Remember, it's very important to remember that these concentrations, when we express the equilibrium constant, we are looking at a state where the reaction is now at equilibrium or now in equilibrium. So it's very important for you to recall that there might be concentration of some species, right, at the beginning, but then it changes until we get to equilibrium. Right, so let's just see. So for a question such as this, the first part is for us to express for the equilibrium constant, to express our equilibrium constant Kc. So we have our chemical reaction, and we can tell, okay, let's just increase its size here. This is our chemical reaction, right? These are our reactants. This is the product. And this chemical reaction can take place in both sides. So what I'd identified as the reactants and the product will swap places in the reverse reaction. So write an expression for the equilibrium constant Kc. We know that our Kc is expressed as a ratio. So we've got a product of the concentrations of the of the products divided by the product of the concentrations of the reactants that are neither solid nor liquid in state. So we have our product, and it is what? It is sulfur dioxide. It's in the gas state, so we will use its concentration, and we have just one product, right? Let me stop this poll. I think we did not have takers for this one. Then after this, we are going to express our denominator. We will not use that just because it actually does not appear, isn't it? It does not appear in the aqueous or gas states. So we are going to list our oxygen, our O2, and its concentration as part of the expression. So this is the expression for our equilibrium constant. The second part, calculate the equilibrium concentration of oxygen if Kc is that. So for question number 2, we have some given data. So these are our data. Let's just collect our data. Our data are as follows. Let me actually do this. I think we have lots of space here. We have lots of space here. We have lots of space here. Right, there we go. Right, let me remove this. Right, good. So the given data are as follows. Kc is actually equal to 6. And the concentration of sulfur dioxide is equal to 3 mole per dm cubed. 3 mole per dm cubed at equilibrium. So we want to calculate the equilibrium concentration of O2. Right. So let's use equation number 1. Right. Using equation number 1. We want to make, using equation number 1, we want to make the equilibrium concentration of oxygen the subject, isn't it? We want to make it the subject of the formula. We want to make it the subject of the formula. So how can you do that? Already you can see that, okay, it's there, it's part of the denominator. So what is the first step? You can cross multiply. So if you cross multiply, what does that give us? So let's just do this, and we can see the cross multiplication here. This Kc is obviously over 1. So our equation is going to change, and then it will tell us that the Kc multiplied by the concentration of O2 is equal to the SO2 concentration multiplied by 1, isn't it? Then what you want is to make the concentration of oxygen the subject of the formula. So that's your concentration of O2 is now equal to the concentration of SO2 divided by Kc. Divided by Kc. Does that make sense to you? Does that make sense to you? This is just a calculation, isn't it? This is just a calculation. So the chemistry is here. The chemistry is here. Then what you are now doing here is the mathematics. So you have just seen that, okay, I want to find this. So it's obviously going to be our concentration of SO2 divided by Kc. The next thing is to now substitute, right? So you've done some algebra here. This was just the algebra. Now you're doing some calculation. So you're just punching in the numbers. What is the concentration of SO2? The concentration of SO2 is 3 mole per dm cubed. What is the value of Kc? Kc is given as a constant. It's 6. So what is 3 divided by 6? That's obviously your half, isn't it? 3 into 3, 1, 3 into 6, 2. So this is going to give you 0.5 mole per dm cubed is the concentration of oxygen. The concentration of oxygen. Does that make sense? So at equilibrium, the concentration of oxygen is simply found by this calculation where you're basing it on the concentration of what? On the given concentration of the sulfur dioxide. Right, let's move a bit fast. Let's move a bit fast and look at another question. Any questions on this one? Any questions on this one? All you are doing is to calculating a reagent concentration. Part of the process involves reagents, and the reagent concentration is what you were looking for. So you now know, okay, in this chemical reaction, then the concentration of oxygen was this much. Okay, let's just look at this. The equilibrium constant is 6. So it's greater than 1, isn't it? The equilibrium constant is 6, is greater than 1. What does that mean? That means that we have a what? We have a higher concentration of the products, isn't it? If it is greater than 1, the forward direction is what is favored. So the formation of the products or of SO2 is what is favored. So this means there is a faster depletion of the S and the O2 into SO2. There is a higher quantity of SO2 as compared to the reactants. So in this case, can you see this? The concentration of SO2 is 3 mole per dm cubed, and there's very little oxygen because the chemical reaction that is in the forward direction is favored. So there are more species here as compared to there. So that is why we are getting that kind of an answer. Very small amount of oxygen. Right. Let's look at another example. So this is what we are doing. We are looking at simple and straightforward examples which give us all the important corners and important points about chemical equilibrium, right? These are the most important pointers or basics for chemical equilibrium calculations. Next week, I want to give you a question, right? Soon after we finish, I want to give you a question. That question, you can actually find it in a past paper, right? So let's just say, look at the question that is in the 2021 paper or the 2022. Okay, let's start with the 2022 is not out. So I was looking for 2021 and 2020, right? So let's look at 2021. So look for the 2021 physical science paper, grade 12, paper 2, and look for all questions that have to do with chemical equilibrium, right? Should be question 6 and one of the first basic one. We've already done one of the first basic ones. So look for question number 6, right? Look for a question that is a full question that has got a chemical equilibrium. We're going to use all these principles in that question, right? Right, so let's iron out the basics. In the next question, all we want is to calculate Kc. Right. So in this question, it reads, for the reaction, SO2 gas plus NO2 gas is equal to NO gas plus SO3 gas. The concentrations of the compounds used are, then you're given all those concentrations. Then they say, calculate the value of Kc. Right. So in the previous question, we used the value of Kc to find a concentration of one of the reactants. Now we are using the concentrations to come up with the value of Kc, isn't it? So let's build our expression for Kc. First. The given data are already supplied, there. So the expression for Kc. In this chemical reaction, let's identify our important items. Number 1, our reactants are on the left-hand side, SO2 and NO2. Our products are on the right-hand side for the forward reaction. All our species are in an eligible phase of matter, isn't it? All our species are in an eligible phase of matter. It means that we can actually use these species for the equilibrium constant calculation. So there we go. So this is our Kc, which is equal to, in this case, the concentration of our NO product multiplied by the concentration of our SO3 product. This is all divided by the concentration of our sulfur dioxide plus, multiplied by the concentration of our NO2. Do we have any ratios that are greater than 1? No, right? So let's just see if the equation is balanced in the first place, because one of the most important things in these calculations is that the equation must be balanced, because we can't afford to proceed and then we are happy and we say everything is fine, yet the chemical reaction is actually not balanced. Because do you notice, if it is not balanced, right, we will need to put in some powers there. So if it is not balanced, it actually means that our calculation is going to be wrong, because we actually have the wrong ratios for A, B, C, and D. So let's first of all figure out if these are balanced. How many sulfurs do we have on the left-hand side? We have one sulfur there. We have no other sulfur there. So we have one sulfur on the left-hand side. How many sulfurs do we have on the right-hand side? We have no sulfur there. We have one sulfur here. So the sulfurs are balanced. There we have it. How many oxygens do we have on the left-hand side? This gives us 2 oxygens plus another 2 oxygens, making them 4 oxygens. How many oxygens do we have on the right-hand side? 1 oxygen plus 3 oxygens gives us 4 oxygens. So for our oxygens, we are balanced and we are happy. How many nitrogens on the left-hand side? We have one nitrogen and no nitrogens there. So we can say one nitrogen. On the right-hand side, we have one nitrogen here and no other nitrogen there. So therefore, we have one nitrogen. So we are balanced as far as the number of nitrogen species are concerned. So our chemical reaction is balanced. So that's the first and important thing. Please don't even proceed. Don't even proceed before you verify that the equation is what? Is balanced. Now we are happy. Our equation is balanced. So we can now be sure that, okay, these are all ones. These are all ones. So which means our Kc is simply this expression, the concentration of NO multiplied by the concentration of SO3 divided by the concentration of SO2 multiplied by the concentration of NO2. Right, so let's substitute. One important thing was that the concentrations of the compounds used are these. So it was important for this part to explain if these are the concentrations at equilibrium. So always look for that, right? And if it's not explained like this, please raise your hand so that your teacher can assist you and tell you if this is at equilibrium. Because when we start any chemical reaction, we've got some reactants. So in this case, for example, we have SO2 and NO2. At time t is equal to 0, we've got those two only. So there's the concentration of NO and the concentration of SO3 is actually equal to 0, right? Then when the clock starts ticking and these two compounds are mixed, then the process starts to yield some products. Now, as time progresses, the concentrations of SO2 and NO2 start to deplete as the products are being formed, right? Until we get to a state where, according to the equilibrium constant, then this chemical reaction arrives or reaches equilibrium. That way we'll know, okay, do we have more or less of the reactants or products? So it's important for us to be sure if the concentrations are for the initial point or the equilibrium point. Now that we're given the concentrations of these products, we can assume that these are the equilibrium concentrations, because otherwise it means that we are calculating Kc for this particular instant where the concentrations are this much, right? So please just be on the outlook for that. Right, so let's now substitute the values. So we've got, what is the concentration of our NO? Our NO, the concentration is 0.4. And we are multiplying that by the concentration of SO3. Concentration of SO3 is 0.2. What is the concentration of SO2? Concentration of sulfur dioxide is 0.2. What is the concentration of NO2? The concentration of NO2 is 0.1. There we have it. So what is the value of Kc? And our Kc is dimensionless because all the mole per dm cubed in the numerator will cancel out with the mole per dm cubed in the denominator. So in this case, we actually have a dimensionless Kc. So let's just punch in these numbers. Let's just see if we've got a calculator somewhere here. So let's blow it up. We're dividing two numbers. At the numerator, we have a 0.4, and then we are multiplying 0.4 by 0.2. So let's just verify in the numerator, do we have the concentration of NO? Yes, 0.4. Do we have the concentration of SO3? Yes, 0.2. So we're happy. Then we divide by the concentration of what? Of SO2, which is our 0.2, right? And then the concentration of NO2, which is our 0.1. So our value of the equilibrium constant is 4. Our value of the equilibrium constant is 4. Right. This answer is telling us that the equilibrium constant is greater than 1, or this ratio is greater than 1. In other words, the products, we have more, the concentration of the products is actually higher in this process, because concentration is just number of moles per watt per unit volume. So if we have the same container, it means everything is in the same container. So at this particular instant, within the same volume, which means number of moles of the products are actually more. Let's look at the concentrations. Do the concentrations indicate as such? Do we have generally higher numbers for the concentration of the what? Of the NO and the SO3. The NO is what? Is 0.4, SO3 is 0.2. How about the SO2 and the NO2? We actually have 0.2 and 0.1. So if you can look, the numbers are actually higher for the products. So this equilibrium constant is actually sensible. It's important for you to check if it actually makes sense, isn't it? Right, let's see if there's someone who has calculated something. Is it making sense to you? Please let me know. Let's also see if, okay, so from next week, I think we will need to have this Zoom link functional, right? We'll need this Zoom link functional just because, yeah, just because right now, I do not have, do I? I do not have the Zoom link app here. Okay, so while you populate your questions, if you want to actually throw them in as we discuss, you can actually verbalize your questions on Zoom. Otherwise, let's jump on to the next question. Is there any question on this one? If you have a question, you can drop it into the chat. Alternatively, you can actually use the group. Let's just see if the group, yes, the group chat is available. Yeah, on the WhatsApp chat. Okay. Okay, so let's move to the next question. Now, we are still on equilibrium calculations, isn't it? We are looking at equilibrium calculations. So the next question has to deal with calculations of what exactly? Let's just see. So this question, and by the way, you can find all these questions and their answers. These are worked examples, isn't it? You find them in the Siyavula textbook. So you can find these questions in the Siyavula textbook. So these are looking simple, but they're actually very loaded questions. They are rich because you look at different aspects of the same concept, right? So they actually help you to revise stage by stage. Now, the next set are calculations, equilibrium calculations. And they give us a question which is like this. They give us a question which is like this. So the question reads as follows. 1.4 moles of ammonia gas are introduced into a sealed 2 decimeter cubed reaction vessel. The ammonia decomposes when the temperature is increased to 600 K and reaches equilibrium as follows. 2NH3 gas decomposes into nitrogen gas and hydrogen gas. When the equilibrium mixture is analyzed, the concentration of ammonia is 0.3 mole per dm cubed. Calculate the concentration of nitrogen gas and hydrogen gas in the equilibrium mixture, and then calculate the equilibrium constant for the reaction at 600 K. I would like to encourage you to do something. Whenever you get a question, first challenge yourself to interpret the question in your own words. Is this question sensible? When you are listening to yourself read it or when you are reading it, does it actually make sense to you? What exactly is happening in the first place? Please have a habit of doing that. Then when you have comprehended the question, the next step is listing the given data, right? So you can write your chemical reaction, check if it is balanced, list your given data. When you've listed your given data, then you can now think about the methods to apply, right? So let's do that. Let's try that. The chemical reaction is already given for us. Let's check if it's balanced. So I'll just rewrite it here and we'll write it as 2NH3 gas is in a chemical equilibrium with N2 gas plus 3H2 gas. So this is our chemical reaction. This is our chemical reaction. Number one, all our participants are in the gas state, isn't it? All our participants are in the gas state. So we are happy. Number two, is the chemical reaction balanced? Number two, is the chemical reaction balanced? So just look at your nitrogens. We have 2 nitrogens on the left-hand side. Do we have 2 nitrogens on the right-hand side? Yes. So the nitrogens are equal on both sides. We have 3 hydrogens on the left-hand side. Do we have 3 on the right-hand side? Actually, we have 3 multiplied by 2, so it's 6 on the left-hand side. Then we have 6 on the right-hand side, which is 3 of these doubles. So we're actually happy that we have a balanced chemical reaction. So the first thing we've established is that the chemical reaction is balanced. Now let's list the given data. They say 1.4 moles of ammonia gas are introduced into a sealed 2 decimeter cubed reaction vessel. So this is our reaction vessel. So let's just say it's sealed, right? So let's maybe put something like that. Right, so they introduce, so maybe they have a valve somewhere there, and then they introduce, maybe let's do it that way, like a valve, right? So we've got a valve somewhere there, and then they introduce this gas. So the number of moles of what? Of ammonia, NH3. The initial number of moles is actually equal to 1.4. 1.4 moles of ammonia gas are introduced into a sealed. Then we are given the volume of the container is equal to 2 decimeter cubed. 2 dm cubed, actually 2.0. Right. So that's our 2 dm cubed. Next, the ammonia decomposes when the temperature increases to 600. So this is the temperature that is increased to 600 Kelvin. It decomposes when the temperature is increased to 600 and reaches equilibrium as follows. So the equilibrium is reached according to the reaction. We've already written it and we've checked that it's balanced, so we're happy. So when the equilibrium mixture is analyzed, the concentration of NH3 is that much. So the concentration of our NH3, this is now the final, isn't it? So this is now at equilibrium. So when the equilibrium mixture is analyzed, the concentration of NH3 is 0.3 mole per dm cubed. 0.3 mole per dm cubed. So we want to what? We want to calculate the concentration of the nitrogen and hydrogen gas in the equilibrium mixture. The concentration of the nitrogen and hydrogen gas in the equilibrium mixture. By the way, for those that like to hear about hydrogen, can you already see this is one of the sources of energy that are being explored in South Africa, where we are working on producing or actually having a plant that will generate hydrogen, many different plants, isn't it? So this is something that you've already seen, right? You can actually have a decomposition of ammonia into nitrogen and hydrogen. And this can become a what? This can become a fuel, isn't it? Gas fuel. Okay, you can also make it liquid, isn't it? You can actually, okay, fine. You can do that later. But anyway, this is what we are given. So we actually have our gas, let's just say these are our gas particles. So obviously it's NH3 that will decompose, so some of them are still NH3. So let's just put that, some of them are still NH3. And then we also have these pairs, which are, so we'll discover how this diagram is supposed to look like, right? So maybe we can actually do that. And then here maybe let's just say we actually have some NH3. Right, so we actually have some diatomic gases, and then we've got the actually 4 atoms, right? Actually 4 atoms. So we actually have 4 atoms there, 4 atoms there. Okay, so we're just trying to have some pictorial arrangement. So when you get a question like this, where you've got some initial number of moles, some final concentration or final number of moles, whichever way, this is where you have to use a Rice diagram. Use a Rice diagram or table. Let's just say table. So for a rice table or a rice diagram, how can we solve such a problem? This R stands for the reaction. So you're going to state the chemical reaction with its stoichiometric ratios. Then, after that, you will need to look at the initial number of moles. So this is the number of moles of the participants at the initial stage of the reaction. So that's the number of moles. We can say number of moles initial. Then this is now the change. So you're now looking at the change in the number of moles according to the stoichiometric equivalence. Then you are looking at the equilibrium. This is now the equilibrium number of moles. So we can say number of moles at equilibrium. And then this would be the number of the concentration at equilibrium. So this is equilibrium, number of moles, equilibrium, concentration. So you can actually come up or use this table format for you to answer such a question, which has a lot of numbers. Okay? So let's plot our rice diagram. Let me just create some space here. Add a new page. Just make it look like that. Right, so let's come up with our rice diagram. So our table should have our reaction at first, our initial quantities, our change in number of moles, our equilibrium number of moles, and our equilibrium concentrations. So let's make it tabular. Let's make it tabular. Make it tabular. Right, there we are. So we have our table, our rice table. Let me just move these there. Right, so on our rice table, we said the first thing is the chemical reaction. So we are just importing the chemical reaction in its balanced state. So this is our 2NH3, which will decompose to 1N2 plus 3H2. So these numbers are the most important numbers. These are the most important numbers. Everything is important, yes. But if you forget these numbers, you might have everything else, but it doesn't count because your calculations are actually based on the stoichiometric ratios or coefficients. So now we have our rice table. So I'll just make the necessary columns per species. The necessary columns per species. So I'm actually supposed to do that, but I don't want to cancel my equilibrium symbol. Right, so there we have our rice diagram. Now what are we given? Initial. So when we listed our data, we already listed the initial number of moles of NH3, isn't it? So the initial number of moles of NH3 is 1.4 moles, right? So this is the initial, we can actually say number of moles at the start, 1.4 moles. They say 1.4 moles of that gas are introduced into a sealed container. So if you are introducing, then there are no moles of what? Of the products. You are still putting these. So they introduce 1.4 moles, and now the container is filled with 1.4 moles of what? Of NH3. Then they heat this chamber. They heat this chamber or this container or this reaction vessel to a point where it reaches 600 Kelvin, right? So you can think about that in degrees Celsius and you subtract 273.15 and you'll see what temperature that is in degrees Celsius. So it reaches equilibrium. Now, when it reaches equilibrium, so there's been some change, right? There have been some changes here, right? There have been some changes. So we can actually figure out the changes based on, these ratios, isn't it? We can actually figure out the changes based on the ratios. So how do we figure out the changes? It's obvious that when we started with 1.4 mole, this is now the change, isn't it? 1.4 mole of NH3. Look at the stoichiometric ratios. We also lost, isn't it, some 2x moles of that gas. Here we gained some x moles of that gas. And here we gained some 3x moles of that gas. Where did we get this equation? We are saying this is the change that is taking place. Initially there was 1.4 and they reduce, this is the reactant, it reduces by its stoichiometric equivalent, because we are still talking the number of moles, the change in number of moles, right? So it's actually 1.4 minus 2 times some coefficient which we will actually calculate. This will lead to a gain of just 1 of those moles, and then this will lead to a gain of 3 of those moles. So we will obviously now need to find the value of x. What is the next thing that we're given? We are given that when the equilibrium mixture is analyzed, so this is now at equilibrium. Remember here we are saying number of moles at equilibrium and then concentration at equilibrium. So when the equilibrium mixture is analyzed, right, the concentration of NH3 is 0.3 mole per dm cubed. The concentration of NH3 is 0.3 mole per dm cubed. That's the concentration. We don't know the number of moles at equilibrium, but we know the concentration of NH3. So the first question now is calculate the concentration of N2 and H2 gas. So for you to find the concentration of N2, this means we are looking for this and that part of the diagram. Any questions so far on what we've done? Does it make sense? Does it make sense to you? We're in one reactor filled with gas, NH3. Then we heat it up, then it starts to dissociate. I think we've done this several times. We've seen this kind of a simulation. I don't need to waste much time. I'll just quickly look for basic chemistry, and we are just heating a gas and then it dissociates. So we've got something like this. Let's just see. I think so. Yeah, I think so. So we just want to make sure that we can see what is actually taking place in the first place, right? So this is the chemical reaction that is taking place. So obviously now with this question, all we need, right? So this is phase changes. I just want to see that. Okay, so we just have some gas and then we just heat it up. So we don't have ammonia here. I'll just choose any gas. So if you just heat it up, then it starts to just change. In this situation, we've actually NH3 which dissociates. So here what we're just seeing is just the dissociation of, in fact, this is just a change of phase, right? It's just a change of phase. But it's similar to something like this. What you'll be seeing is NH3 which when you heat, it starts to tear apart. So that's what's taking place. So the question actually requires us to find these two concentrations. So how can we find the concentrations? It's obvious that basically, the concentration is given by the number of moles over the volume. The volume is the same. This container has not been changed, right? So the volume is the same. This means the number of moles, the concentration of our N2, let me just move this. The concentration of our N2 is going to be the number of moles of N2 divided by the volume. And the concentration of our H2 is going to be the number of moles of H2 divided by the volume. So it's one and the same equation. Do we know the volume? Yes, we know the volume. From the given data, the volume is what is supplied. So for this chemical reaction, for this calculation, the denominator is telling us that everything is given. How about the numerator now? The numerator, we need to find the number of moles. We need to find the number of moles. And how can we do that? We can now use this part of the Rice diagram. How can we find the number of moles? How can we find the number of moles? So for us to find the number of moles, already we can see that we've already figured out the stoichiometric ratio of the change in moles, right? So obviously we're going to lose that much and we'll gain that much and that much of the product. So we can actually take advantage of what is given. This we know, isn't it? And this is given. We know we can relate this concentration to that number of moles, isn't it? There's been a change. So these are the remaining number of moles, right? And then that is what we're actually going to find there. So we can actually first calculate this X using the concentration. Right, so how are we going to do that? We know that the concentration of NH3 is equal to the number of moles of NH3 divided by the volume, isn't it? Number of moles of NH3 divided by the volume. And we actually have a number, isn't it? Remember, we want to look for this so that we can find our X. So we actually have a number. This concentration is given, isn't it? They gave us this number. This volume is given. We've already seen that the volume is what is applied. So from this chemical reaction, from this mathematical equation, this implies that the number of moles of NH3 is actually equal to the concentration of NH3. This is now at equilibrium, isn't it? Multiplied by the volume. That is the number of moles at equilibrium, which is that part of the Rice diagram. So it's actually guiding you, right? It's giving you some ideas on what to calculate next. So let's put in the numbers. What is the concentration of NH3 at equilibrium? 0.3 mole. So maybe let me actually take this equation here. Let me take this equation here. Let's do that so that we can use all the space. Right. Okay. So this implies that our number of moles is 0.3 mole per dm cubed multiplied by or times our volume. We said our volume is 2.0 dm cubed, right? So dimensionally the dm cubed will cancel out, and we now have 0.3 times 2, which is 0.6 moles. So we actually have the number of moles of NH3 when at equilibrium. So let me just put an equilibrium sign there. So this is our number of moles at equilibrium. Then you jump into the Rice diagram. Number of moles is 0.6. We have found the number of moles. So if the number of moles at equilibrium is 0.6, this means we can actually find this unknown X, which is representing the change, right? We can find the unknown X, which is representing the change. So next step is to find X. Why are we trying to find X? Because X is our answer. Can you see? Whatever value of X is going to be actually the answer there. The value of X is going to be the answer. We multiply by 3 there. Then we get these ones. It's obvious. We just use the equations that we've already figured out. Because of that, it means we actually end up getting the answer from these stages. So to find X, we can now use the first part, isn't it? We can use the first part. If the change in number of moles is given by this, 1.4 moles minus 2 times X is actually equal to 0.6. Then this means we can actually find the change in number of moles. So let's build that equation. 1.4 minus 2x is equal to 0.6 moles. 1.4 minus 2x is equal to 0.6 moles. So what is our x? So you can now do some mathematics here. This means that your 2x must be equal to 1.4 minus 0.6. Your 2x must be equal to 1.4 minus 0.6. Let's add another page there so that we can continue with our calculation. Is it making sense to you? Is it making sense? Okay, we are out of time now, so I'll try to be a bit fast. I think we already know where we are, so we can quickly catch up. So the next step, what is the next step? You already have this equation. Your next step is to now do your mathematics. What is 1.4 minus 0.6? That should give you your 0.8. 0.8, and that's your 2x. This means your value of x is actually equal to, what is 0.8 divided by 2? That will be 0.4. So that's your value of the unknown x, which is it's any number. It's a coefficient that is representing the change in number of moles. Now that you have x, you can go back to the Rice diagram. We're going back to the rice diagram. Our x is equal to 0.4. This means on this part, the change is what? 0.4 moles. At equilibrium, we now have 0.4 moles of what? Of nitrogen gas. And then 3 multiplied by that 0.4 is what we have here. So 0.4 multiplied by 3, that will give you what? 1.2, isn't it? 0.4 multiplied by 3 will give you 1.2. So our rice diagram is filling up, right? It's filling up. Now we know that by considering the change in the number of moles during this chemical reaction and calculating the number of moles for a given concentration, we could actually come up with the number of moles of the products. So now let's finish up. Finishing up means we're now calculating this unknown and that unknown. We already have the mathematical reactions here. The concentration is simply equal to the number of moles divided by the volume, right? So let's put in the numbers. So here it's equal to number of moles of nitrogen. What is the number of moles of nitrogen? Our number of moles of nitrogen are actually 0.4 moles. So that would be 0.4 moles divided by 2 dm cubed. What does that give you? On this part is going to be equal to number of moles of hydrogen, that is 1.2 divided by 2 dm cubed. So what are you getting? What are you getting? Your 0.4 divided by 2, you should get a 0.2 mole per dm cubed. Mole per dm cubed. This calculation should not be mixed with the next one. 1.2 divided by 2, that would be your 0.6 mole per dm cubed. 0.6 mole per dm cubed. So you have calculated the concentration of your nitrogen gas and the concentration of your hydrogen gas. You have used the basic equation that says concentration is equal to the number of moles over the volume. The volume of the container did not change. It did not change. So you have 2 dm cubed there, you have 2 dm cubed there. The number of moles, you use the rice diagram, right, to come up with the 0.4 moles and the 1.2 moles for the hydrogen. Then you complete your calculation. You know, okay, these are my number of moles for the hydrogen and the nitrogen. So let me give you a challenge now. Calculate the equilibrium constant for the reaction. Calculate the equilibrium constant for the reaction. This one we've done it before, isn't it? So when we meet next week, I want to know that. Then our homework. So our homework is as follows. Our homework. So number 1, we had said, what did we said? Just now we said question number 2. So calculate the equilibrium constant for this reaction. Then number 2, attempt the question, the equilibrium question. I think it's question number 6. I think it's question number 6 of the, which is in the 2021 November exam paper. So let's just say paper 2, November paper 2, right? So these are your 2 pieces of homework, right? So calculate KC for this question that we have already done. You can just go onto the CFL textbook and you'll actually see how they do it for you. It's important for you to do it first, right, before you even look at the textbook. Then you can now come up with the, you can now attempt the question, right? You can now attempt the question, and then next week, let's attempt it, right, so that we can clear out some equilibrium questions and calculations. So it means that we will come back to our acids and bases. Remember, we said we want to finish with acids and bases, but that's the purpose of these tutorials. If your question has not been answered, there's no point for us to continue or to proceed. So you send us the question, then we'll actually have fun and work it out and try to answer any other associated questions. And then when you've done that, then we can then proceed to the next if there are no questions during that week. Okay, so this is the end of our tutorial today. I hope you learned something, right? Let's meet next week, same time, so that we can have some fun with some chemistry. So all the best, and questions, please. Let's meet next week. Sharp, sharp.